Welcome back, everybody. So this is Rajesh's third lecture. He's going to tell us about string duals to free field theories.
Okay, good. Let me now change gears from what I was talking last time, which was about the general approach to try to understand, derive gauge string duality, starting either from looking at it from the point of view of string theory through open-closed string duality, or from the point of field theory to try to naturally to take this TOF idea ahead in trying to find a natural way to come up with a field theory, from field theory to string theory. But so today what I will, so that was fine and very general, but it always helps to have some concrete cases where one can try to see how these work. So, so what we will do is to talk about two cases of concrete realization of the duality of tensionless AdS string theories with free CFTs. That means so this the coupling equal to 0. So the first one, which is in a sense the better understood one, is one involving AdS3, specifically this background with k equals to 1 unit of NS flux. And that's what corresponds to the conformal, to the tensionless limit. And this is dual to a symmetric product CFT. Symmetric product orbifold CFT, which is a free CFT. It's just taking n copies of the T4 CFT and orbifolding by the symmetric group, and will be in the large n limit as always. So that's the first example, which I will briefly kind of mention, describe, because it will be more for in these lectures. This will be more of by way of motivation of the case of AdS 5 times S5 in the tensionless limit, which corresponds to free n equals to 4 spin-angles. So I had given the link for the lectures that I gave in Seoul last month, which was about the part A, but I'll just very briefly describe some of the features which naturally generalize to AdS 5 times S5. In both cases, the world sheet theory is a gauged linear sigma model. I mean, if you don't know what that means, don't worry. It's basically, we'll see it's a free theory with a kind of an underlying gauging. The main point is that the fields are sort of twister-like twister variables. I won't have time to explain the twister geometry part, which is something I think we are still understanding, especially in the case B. But the underlying fields that we will be working with are these sort of twister variables. So that's the case that I will be mostly focusing on. So let's start with the case A of AdS. times T4. So here we, in a way, have a very clear idea what the tensionless limit is. So this is essentially mostly work with Eberhard, Matthias Geberdiel, and so in the last few years, I think we made a proposal for what the tensionless limit of this theory is and how to describe it from worldsheet point of view. So I will summarize that very quickly. So the theory with k equals to 1, that's the smallest amount of H3, the Nevers-Schwarz H3 flux, is the tensionless limit. And in some sense, you can believe that because it's sort of the smallest radius you can have with NS/NS flux. So this is the tensionless limit. And so from the worldsheet point of view, this worldsheet theory can be very described in a conventional way because it has only NS/NS flux. And in fact, for the general case with NS/NS flux, there's an alternative description to the usual RNS worldsheet description. And this is in terms of, so it's what is called a hybrid description. And this is in terms of Bezumino-Witten theory, which I will explain some more. So worldsheet theory. So this will describe the ADS3 times S3 piece. And then there is times T4. In fact, it's a topologically twisted T4. And some course. And I won't go into all this. You can see more details in my lectures, as I mentioned. I'll focus more on this, this part which describes the, so this is the piece which describes the ADS3 times S3 piece. And there's the T4 piece is sort of trivial, and then there's some ghosts, etc. Those won't play very much of a role. All the interesting physics is in the ADS3 times S3, which is captured by this Bezumino-Witten model. So let me say a little bit about what this PSU 1,1/2. You can think of it, it's a super group. So it has bosonic components and it has fermionic components off diagonal. And the bosonic piece is the bosonic subgroup. There's a SU 1,1, there's a SU 2R. So this is nothing but nothing but the SL2R of the ADS3 isometry, and this is the R symmetry of the S3 coming from the S3. So in the dual field theory, it's an R symmetry. And then there are these supercharges on the off diagonals. So this is a fermionic group, and you can define the property of a supergroup very much like an ordinary group. So except that you have these Grassmann entries in the off diagonal, so that's what the /2 represents. So these are the two. There are the two bosonic pieces, and then there's the off diagonal piece here, which connects the two, which are in sort of the supercharges. So this is the general statement about the supergroup. So the PSU, I mean, so in a supergroup, there are this P. You can talk of a U1,1/2, which we will describe, in fact, shortly, which is the analog of the UN group. But then you can project by two U1s. In this one is sort of so there's a U1 associated with the diagonal here, and the U1 associated with the diagonal here. And you can take the sum and the differences of those two U1s, and those, when you sort of mod out by those, so one of them corresponds to imposing sort of the super determinant is equal to 0, or at the Lie algebra level, the super trace is equal to 0. That's what you call the S. And the P is like a projective, this thing, which is the overall U1, and the sum of the two U1s is equal to 0. So that's that's the sort of PSU 1,1/2 sort of notation. So what we have, so this was, as I think I should have mentioned, this was the statement, I mean, so it was Berkowitz, Waffa, and Witten in 98, I think, that they proposed this hybrid formalism to describe ADS 3 times S3. They were mostly interested actually in the case with Ramond flux, but their description in the case of pure NS flux gives it in terms of a Weisser-Witten model, and you have k units of NS flux. It's at level k. Somehow all these years, the level 1 theory had escaped particular attention, but now we see that it is actually very special in many ways. It corresponds to the tensionless limit, but from the worldsheet point of view, also there is at level 1 there's a simplification. The PSU 1,1/2 has a free field description, or a free field realization. This is a bit like for the SU2 or U2. So what is this free field realization? There are two complex fermions which are canonically conjugate. Pairs. So you have here alpha, beta, take values plus or minus. So there are so you have so psi plus is conjugate to chi minus, and psi minus is conjugate to chi plus. That's what this epsilon tells you, and R and S are the mode numbers, which can be integer or half integer, depending on whether you're in the Neves-Schwarz sector or the Ramond sector. Okay, so these are holomorphic fields. So by the way, this is, like I said, it is for, in SU2, some of you who have studied CFT, two-dimensional CFT may know that the SU2 or the U2 level 1 CFT has a realization in terms of free fermions. And this is a sort of a generalization of that. And I will explain exactly what I mean by that very soon. So there are also bosons, and two complex and sort of first order bosons. First order means that they are first order kinetic terms, because they're kind of like a beta gamma system for those who know the Polchinski notation. So beta gamma system with lambda equals to half. or spin half. That's what I've written here. So what that means is that these bosons have are also they're kind of like these fermions, except that they obey commutation rather than anti-commutation relations. So they are essentially the same as the fermions with opposite statistics. So psi plus is conjugate to eta minus, and psi minus is conjugate to eta plus. So that's the if you wish, if you wanted to write down an action, they would obey first order. They would have a first order term, which is something like psi plus del bar eta minus or something like that, and similarly psi minus del bar eta plus. So they are holomorphic fields. Similarly, the fermions. So I will be talking only about the left movers. There will be a similar thing for the right movers as well. Okay, so the point of this free field realization is that from these free fields, we can construct the generators of U1,1/2 at level 1, and these are just bilinears in these free fields. So, for instance, let me just write down some of the expressions so that you see it's very concrete. If you have not seen these sort of free field realizations before, they're very useful in two-dimensional conformal field theory. So these are the generators of SU1,1 or SL2R. You have J3 and J plus minus. They're just made into, so J3 is some neutral combination involving eta plus eta minus. J plus minus involves, J plus involves eta plus psi plus, and J minus involves eta minus psi minus. This is
just to clarify, Rajesh, this subscript M is eta plus M psi minus M, not
the whole thing. I mean, each of them will have modes. So this is really the mth mode of the product.
Mth mode of the combination, I see. Okay.
Yeah, so it will be actually, that would make it more cumbersome to write. It would be something like eta plus R psi minus M minus R sum over R. Yeah, so this is just a short form of that. Correct. So maybe I write this. So this is something like this.
This sum is a normal ordered sum, right? The one.
Yeah, this would be a normal ordered sum. All sums would be normal order. So that's the SU1,1. Similarly, the SU2, the R-symmetry generators, there's a similar expression, but so this was involving only the symplectic bosons, so these free bosons. The SU2 involves only the fermions, and in fact, that's the usual kind of construction and that you have for SU2 or U2. And as so these would be the generators of SU2. And then there are 8 supercharges. Some S alpha beta plus minus M, and these involve 1 fermion and 1 boson. So that's so I'm not writing out explicitly, but you can, there'll be similar expressions involving chi plus, psi minus, and so on. The point is that these, once I specify the commutation, anti-commutation relations of the, once I've specified these, I can construct these bilinears and verify that these obey the commutation relations of U1,1/2 at level 1. And so that's what you mean, what I meant earlier when I said that you get a free field realization of the level 1 theory, that these obey the commutation relations which of the Kac-Moody algebra, which corresponds to the level 1 theory. So to go to PSU1,1/2 at level 1, one can quotient by a sort of a central term, which is made out of the 2 U1s, like I said. So you can write this U1 generator, which is something like this, eta plus. It's the opposite combination to the J3. And BM similarly is the other one. So you see, this is almost very close to what J3M and K3M are, but it has an opposite sign. That's like the Cartan, being the Cartan generator, is like 1 - 1. This one is like 1 1. So so these are sort of 2 U1 generators, and the sum is actually a central term, and you can quotient by that. So by that, you mean that you consider only the states which are annihilated by these modulo the descendants. So that in a way imposes the whole PSU 1,1/2 condition.
These U1s are compact?
These, so I mean, at the moment, I'm not really, I'm working at the level of the Lie algebra and the Kac-Moody algebra. So, but if I were to think of the full group, yes, they would be compact. But I'm not using that in any way here.
Okay. Okay.
And yeah, I'm not sensitive to that by working at the Lie algebra level. So this is what we will use, this free field realization. Together with its what is called and its sort of spectrally sectors generate the physical states. Of the string theory, of the world sheet theory. So I should very quickly tell you what the spectral flow is. Again, I won't have time to go into it in detail. So supposing we start with the NS sector. So the NS sector corresponds to fields which are annihilated by all positive modes. And the NS vacuum is one which is annihilated by, and similarly for the fermions, all with R when R is greater than or equal to half. They annihilate the vacuum. So that's for how you define the NS sector in the conventional way. But now to define the spectrally flowed sectors, I do something at first sight a little funny. So I define a new set of field modes. What I'll call the Tilde modes. So these are ones where these are modes with a tilde, which are just the same as the original modes, but with some shift in the mode number. So we define this, define these spectrally flowed modes for all the fields, and they're just shifted up or down by plus minus W by 2. So why have I done this? This I'll motivate it in the following way. But there are many ways to motivate it. But mathematically, one way to motivate it is that if we consider the bilinears as above, but in terms of the tilde modes, so imagine I define J tilde, J tilde plus minus J3 tilde, K tilde, and S tilde, and U tilde, V tilde, etc. What by that I mean just replace each of these by tildes. Wherever there are any fields, you replace them by the corresponding tilde fields, and you get a set of generators, right? Now these tilde fields, by the way, also obey the same commutation relations as the original fields, because you see that this psi plus is conjugate to eta minus, and one is shifted up by plus W by 2, and the other is shifted down by minus W by 2. So they still remain conjugate to each other, and they satisfy the canonical commutation relations. So the bilinears that I built from these tilde modes, they will also obey the commutation relations of U1, 1/2 level 1. Okay, so that's because I only use the commutation relations of the basic fields to show that this thing. And so this is so these redefined fields will also obey the same commutation relations. Well, you have something to check, which is to do with the normal ordering, and that Sumangshu was this thing, that the new fields will have a slightly different normal ordering, but indeed they will all cancel in such a way that the bilinears will actually also obey the same algebra, but the individual generators, their relation will be a little different. So you'll have like J tilde M, if that's the left-hand side is defined by the bilinears. So J tilde 3M, for instance, is this minus half. And so, and similarly for the S's, which I'm not writing, that get shifted up and down by half W. So what I was saying essentially was that the J tildes will also obey the same commutation relations if they are related to the J's in the following way. So this is what is called an automorphism of the Lie algebra or the affine algebra. That if I redefine new generators of the Kac-Moody algebra in this way, they are non-trivially related to the old generators, but they still satisfy the same Kac-Moody algebra. So that's a property of the spectral flow. So the spectral flow is what is called a non-trivial automorphism of the Lie algebra. So normally this doesn't do very much, but in the case of non-compact groups like SL2R or more generally something like this PSU 1,1/2, something very interesting happens because the representations are infinite dimensional. The unitary representations are infinite dimensional. And so you can actually generate new representations, which are not highest weight affine representations through by considering the action of the spectral flow in the following way. So we can define a spectrally flowed vacuum in the sector W. By the way, I forgot to mention, W will take to be sort of in the positive integers. So that's of course important so as to maintain the mode numbers. But you can see here that when W is even, then you go from Ramond to Never-Schwarz to Ramond or vice versa. And when W is odd, sorry, when W is even, it remains Never-Schwarz goes to Never-Schwarz, Ramond goes to Ramond, because the fields continue to remain the same what they are, the mode numbers. But when W is odd, then it takes you from a Never-Schwarz sector to a Ramond sector or vice versa. So we define the spectrally flowed vacuum such that it in the sector labeled by W such that it is annihilated by the positive Tilde modes. So the positive Tilde modes, so for instance, psi tilde plus minus R, eta tilde plus minus R. So all these and some of and the fermions, all of these annihilate the vacuum for R positive. So this is independent of whether it's in Ramond or Never-Schwartz. So we can define this sort of spectrally flowed vacuum in this way. But now you see in terms of the original modes, the untilde modes, because of this shift, we have something funny because what were normally we started with the Never-Schwartz sector, and these positive modes were annihilating the vacuum. So you could, if you wish, think of these as like the annihilation operators, and the conjugates, which are the negative modes, would be the creation operators. And that's what you normally do in string theory. You then create a Fock space on this vacuum by acting upon by the negative mode numbers, and you generate the Fock space from them. So here we impose, so we now consider a new, the spectrally flowed vacuum, which is in which the tilde modes, the positive tilde modes, we think of as the annihilation operators, and the negative, the modes with negative, tilde modes with negative mode number, we think of as the annihilation operator, as the creation operator. But because of this funny shift, because we have shifted things here, what is positive here is not necessarily positive with respect to the this thing, and vice versa negative. So what you have is something which is so you have, for instance, the following. You find eta plus R or psi plus R, these things acting on the vacuum, is not equal to 0 for things that you might otherwise have thought. So these are some positive modes. The first W minus W by 2 or so, or W minus 1 by 2 positive modes, they sort of don't annihilate the vacuum, as you can just see. So this is just so in terms of the original modes, which are really the physical modes. So this is, if you wish, like a trick. The tilde modes are like a trick to generate a new representation, because since they obey the same commutation relations, you know that supposing I define a representation by this, then that will give you a representation of the affine algebra. But in terms of the original modes, that's a somewhat funny representation, because there are these positive modes which do not annihilate the vacuum. And at the same time, there are some negative modes also which annihilate the vacuum. Normally, negative modes wouldn't have, but these negative modes would annihilate the vacuum. So, so yeah, here I think I should have put so so this is the thing which is a little bit unusual, and therefore these modes, these first these W modes in this range. So it makes sense to kind of divide. So we define two sets of modes in terms of my original untilde variables, namely eta plus minus r psi plus. I'm not writing the fermions. There's similar thing also for the fermions, but if we can consider firstly these modes up to r is equal to minus w minus 1 by 2 all the way to plus w minus 1 by 2. We'll call these the wedge modes. So there are these, and then there we'll define all the rest of the modes, where that is r is less than minus w minus 1 by 2, r is greater than the plus w minus 1 by 2. And these we'll call out of the wedge modes. So if you wish, this terminology of wedge is a bit coming from the following, that if I were to sort of think of the mode number r over here and the spectral flow parameter over here, and so you have modes. This is sort of r is equal to plus w minus 1 by 2. And so this, so it's, well, I should probably shift it. This is w equals to 1. So this is really, this is w equals to 0 here, and this is w equals to 1. So yeah, well, I think I messed it up. The intercept is at w equals to so this is 2r. So w equals to 1. It is r is equal to 0. No, so it was right what I wrote. Oops. Yeah. So in any case, let me draw it. So this is r, and so w equals to 2. You'll have some modes here, and so on. So there'll be always a finite number of these modes. So the wedge modes are the modes here in this wedge. And but of course there are all these other modes here which are kind of so so these are the out of the wedge modes. Out of the wedge modes here. So that's this thing, and so the nice thing about the I mean, in the wedge, what you have is now some of these modes which are positive also annihilate. So for half of them, all the modes in the wedge create so for instance, what I wrote over here, so here you can see that for eta plus and psi plus, all the modes in the wedge will not annihilate, they'll act as creation operators, and all the modes in the wedge of the psi minus and eta minus will act as annihilation operators. So so the roles are sort of reversed. The modes get sort of slanted, and in some sense the wedge modes can be thought of as the act in as some kind of generalized zero modes. In fact, for W equals to 1, you see that R is 0. So the wedge mode is indeed a zero mode. So W equals to 1. In fact, this is the Ramond sector. So the Ramond sector can be viewed as sort of one spectrally flowed unit of the Neveu-Schwarz sector. And that's so you're kind of creating more zero modes by acting on the spectral flow. So so in W equals to 1, they are what you normally think of as the zero modes of the Ramond sector, but in many ways the wedge modes behave like zero modes, even for the other cases. Or another way to say it is that what might have been a zero mode gets shifted along this line along, and so the spectral flow kind of takes zero modes along these lines, and you kind of open up more zero modes, and so these kind of create states which and in the symmetric orbifold so this is a general statement about spectral flow, and in the AdS3 string theory, and I don't have time to explain this, these spectrally flowed states they correspond to the W-1th twisted sectors of the dual symmetric orbifold. So in the symmetric orbifold, in the large N limit, the cycles, the twisted sector states of the orbifold are labeled by the length of the cycle, and W-1, the Wth spectrally flowed sector of the string theory corresponds to the W-1th twisted sector of the dual orbifold CFT, where W equals to 1 corresponds to the Ramond vacuum, which is the untwisted sector, and W equals to 2 corresponds to the W equals to 2 corresponds to the untwisted sector, W equals to 3 corresponds to the Z2 twisted sector, and so on. Okay, so this is
Rajesh,
yeah.
I mean, so there was this puzzle at one point of time that, you know, the chiral primaries truncate if you just use the symmetric product to the n or something. I mean, if you stop at n, they truncate.
Right.
But in this bulk, now you have like, it goes on forever, right? I mean,
yeah, so that we won't see here because we are in the purely perturbative domain, and that truncation is like order n.
And
so it's sort of non-perturbative from the point of view of the bulk. So yeah, so we don't see that stringy exclusion type of truncation.
right, okay.
It's an interesting question whether there is some signature of that. I mean, it's a bit like these trace relations also. The same question also arises in the Yang-Mills theory. And in what way can you see some trace relations? And I think it has to also do with this sector with D branes and this thing, but I don't have a clear picture of how you might try to see it from the perturbative world sheet point of view.
So here you're like, as though you're an n goes to infinity, basically.
Yeah, so we are strictly sort of in the, or in a 1/n expansion, but you can do it in perturbation theory, but there's no real sense in which, we can see finite n. And so that would be interesting, but the world sheet, that's the limitation, of course, of the world sheet description, that it doesn't see these sort of effects.
Okay, thanks.
So I'll just say one more point about the symmetric, I mean, the AdS3 case, because I want to use this only as a sort of a stepping stone to the AdS5 case. But just one point I wanted to note here is that the tensionless theory on AdS3 times S3. So the AdS3 times S3 piece is essentially topological. So what I mean by that is that there are no degrees of freedom, propagating degrees of freedom on the AdS3 times S3 piece. So why? Because normally the PSU 1,1/2 level K theory has 3 plus 3 bosons. This is from the, the SL2R plus the SU2. And 8 fermions. So these are the off-diagonal elements. So this is 6 bosons and 8 fermions. This is what is how you would normally have in for general K, and in particular large K corresponds to almost flat space theory. So here you would have this, and then the T4 theory has 4 bosons and 4 fermions. So total of 10 bosons and 12 fermions in the matter sector. That's what the matter part of this string theory would be, would have been in general. But then you have ghosts. So you have 2 bosonic ghosts in the usual way, which removes 2 transverse degrees of freedom, 2 bosonic ghosts. And it turns out that in this hybrid formulation, you essentially have 4 fermionic ghosts. So you subtract this from this, so you get a total of 8 boson plus 8 fermion physical degrees of freedom, and that's what is the normal thing in a 10-dimensional string theory. But for the level 1 theory, it is drastically different. Because we saw that the U1,1/2 level 1 theory has 4 bosons and 4 fermions. And then the PSU 1,1/2 level 1 theory, you remove 2 U1s, so it has 2 bosons and 4 fermionic degrees of freedom, and this is cancelled by the 2 bosons and 4 fermion course that we had earlier. So I just the Gauss degrees of freedom are the same. So you exactly cancel off these 2 bosons and 2 fermion. So you have 0 physical degrees of freedom. So of course, there is the T4 is there, T4 excitations. You still have 4 bosons and 4 fermions, but it's much less than the 8 bosons and 8 fermions that you had in general. Now, effectively, if you consider the full 10-dimensional theory, there's only there are only 4 bosons and 4 fermions, and in some sense, in the ADS 3 times S3, there are 0 physical degrees of freedom. Okay, so this is something very somewhat unusual, but it is consistent now. We see with many things. Actually, you look at the partition function, you look at the so this is I just made a very hand-waving counting here, but if you look at the partition function, you see this very explicitly, that you get essentially only these 0 mode contributions. So there are only these generalized 0 modes. Or these wedge modes. Contributing from so only a finite number of these modes for any W contribute to the partition function. Of course, the T4 part is there, so in some sense you get like the T4 excitations, you get that part of the spectrum, and that's what agrees also with the symmetric orbifold of T4. But this is how the counting works. Okay. So now let me start on the ADS 5 times S5 case, but are there any quick questions? I just sort of just wanted to mention some, I didn't really do justice to the ADS 3 times S3 case. And there are many things one can say about that, about the partition function and so on, like I said, and the matching of the spectrum, and furthermore go on to the matching of the correlators, which also we succeeded in how to understand them in some geometric way. Those are some of the things I think I've covered already in these other lectures, so I'm not repeating them. One other thing I should probably have said is that these, I mean, it's not so obvious here, these were just some free fields that I considered, but and this will become more obvious in the ADS 5 times S5, where we will generalize that these will be essentially like the twistor degrees of freedom. So that's why so this will be like the super twistor degrees of freedom. So there'll be a direct analog of this, and that's why these were being called twistor sigma models. Okay, any quick questions or comments?
I have a question. Maybe it's not exactly related to what you have talked about so far. Is there a bosonic string version of this AdS3 times S3 times T20 at k equal to 3? Because here you are using that there are these fermions and this supergroup formalism. There is no such thing in bosonic strings.
Right. Right. I mean, I guess you could try to. It does seem like a critical string background, and k equals to 3. There are definitely interesting things that happen even in the bosonic string on AdS3. It does seem like a tensionless limit. But I don't know whether this continuum that is normally there, whether it will go away in this limit. Yeah, there may be some way to define a theory which has only the bottom of the continuum, but I hear supersymmetry kind of does it for you very naturally. This free field realization does it, but maybe I haven't thought much about it, I should say. So you will get an SL2R level. I mean, if you have K, the bosonic level is K, then you have a SL2R level 3 theory, which doesn't really have a free field realization, I think. Yeah, so I don't know of a simple way in which you can have a free field realization and a well-behaved spectrum and so on.
Okay.
Yeah. Okay, so there's a natural generalization of this of the AdS3 times S3 case. To AdS5 times S5, which now has the isometry PSU 2,2/4 instead of PSU 1,1/2. Well, I should have said in AdS3 times S3, it's PSU 1,1/2 times PSU 1,1/2. That's the left movers and the right movers. And now we have PSU 2,2/4 is the space-time isometry. So so the natural generalization is to consider 4 free fermions and their conjugates plus their canonical conjugates, and 4 free bosons. Similarly, these sort of symplectic bosons plus their conjugates. So in other words, let me denote the bosons by lambda and mu. So mu dagger. So the daggers here don't refer to the adjoint or complex conjugate. They're just different fields. So it's a bit unfortunate notation that we picked, but kind of stuck with it now. And similarly, you have another set, mu and lambda dagger. So here, let me explain the indices. The alpha and alpha dot take in values 1 to 2, and they correspond to SU2 times SU2, the usual SU2s in the Lorentz group. So this in the space-time, which belong to the space-time group, but here we think of them directly as sitting inside the PSU 2,2/4. But in the space-time Lorentz group itself sits inside the SU 2,2, which is the same as the four-dimensional conformal group SO 4,2. So that's this SU2. They're essentially these two SU2s, which sit in this bosonic part of this. So once again, the picture is what I had written before. You have this PSU 2,2/4 has SU 2,2, and here there'll be an SU4. That's this PSU, the /4 piece, and then there will be the off-diagonal super charges. So that's what the alpha corresponds to, and the A goes from 1 to 4, and that is in the SU4, which is the R-symmetry, as you know, in the dual CFT. So, so these are the various indices. So you see this lambda and mu and lambda dagger and mu dagger are the bosons, and psis, there are 4 of these psis, and they're conjugate psi daggers and canonical conjugates, and those are given by these. Okay, so we have just doubled the number of degrees of freedom of the previous case, and just slightly changed the notation. But essentially, you see the fermions are the usual first order fermions. The bosons also are. We'll again take them to be spin half. I should have said here spin half. So they are also like a beta gamma like system. But now actually it's more easy to see a sort of a geometric picture. That you can actually assemble these into what are called Ambi twistor fields. This is use the notation of Berkowitz, and I'll just say in a moment the context. So all the dagger fields you can assemble into one big field, and it has components of so this, if you wish, these are in the vector representation of PSU 2,2/4. The first 2 components are bosons, and the last 4 components, first 4 components are bosons, and the last 4 components are fermions. So, so they are both vector and conjugate vector, fundamental and dual fundamental. So. So these, in fact, are what are called ambitwistor fields in the twistor literature, though, as I said, I won't be saying very much about the geometric interpretation right now, because that's still sort of being understood, but there's definitely an underlying twistor picture here. And it's not a coincidence that these fields appeared in this context earlier. This was Berkowitz proposed a field theory of open string worldsheet theory to capture the scattering amplitudes, perturbative scattering amplitudes, or actually only tree-level scattering amplitudes of n equals to 4 super Yang-Mills by writing this string action. So in some sense, free action based on these fields. So what we are actually doing is in some ways a closed string version, though Berkowitz had additional things because of his this thing. So so these fields are there in common, but he had some additional current algebra, and he had only a certain set of bosonic course. So we will be treating this as a superstring theory. So this twistor description, this is all that I'll probably say about the twistor description right now, but it's a useful way to think of these fields. And but independently, we can just consider bilinears. You can pick the different bilinears, one Y and one from Z, and just as in the case of ADS3. And you construct normal ordered combinations of these. So these are again purely purely left movers. You just construct some normal ordered combination of these, and what you find is that they generate U2,2/4 at level 1. The Kac-Moody algebra of U2,2/4, and there is if we mod out by a central term, which is generated by the sort of the diagonal, the U1, the YI, ZI, then this is the analog of what I had called Z earlier in the, or U plus V in the earlier language, but now we'll call that this C. So if we mod out by this, we get so what are these? So this is so what we have defined here are some fields which generate this level 1 Kac-Moody algebra, and in fact this is a current algebra version of the oscillator construction of PSU 2,2/4 of just the global algebra PSU 2,2/4. Just like SU2, there is this oscillator construction you have probably read in Sakurai's book and so on, Schwinger's famous oscillator construction. People have generalized that to many groups, and for PSU 2,2/4, there is an oscillator construction, which I guess in some ways goes back to Dirac, but I guess more recently by Gunaydin and Marcus and so on. And this oscillator construction has been used in these spin chain formulation of n equals to 4 Yang-Mills. And for instance, in the work of Bicert, And in some ways, very close realization of these was in work of Alde, Justin, Gava, and Narayan. These oscillators are some ways good building blocks for the n = 4 Yang-Mills field. But here we are now talking about a current algebra of these oscillators, which we are proposing from a worldsheet description. But you can already see from that this is sort of perhaps the natural language in which to think of the worldsheet theory. And in some ways, this paper of Justin, etc., was trying to achieve that kind of description. So let me now just set the stage for next time when I will talk about how talk about the quantization of this string, or at least the proposal for how to quantize it. But first, let me this thing again, the spectral flow in this context. So just like in the AdS3 case, the spectral flow is the crucial ingredient, I think, of the worldsheet theory. So we again start with the NS vacuum, the Navier-Stokes vacuum, and the mode numbers are therefore half integer. All the fields are half integer modes, and this vacuum is annihilated by all the so now you can define again these tilde modes and these spectrally flowed modes, and I'll just let me just cut and paste. Yeah. So you just move some of the lambda. So the left-hand side are the tilde modes. I moved the mode number R up or down by plus minus W by 2, very much like in the case of the AdS3. So you see that lambda and lambda dagger move down by minus, and mu dagger move up by plus. And similarly for the size, two of the size move up and two of the size move down, and so on for the side dagger as well. So we have again the same logic as before, the bilinears in the tilde modes generate U2,2/4 at level 1, but these things are slightly different. The generators will be shifted, and I'll write down some of the expressions, but we can consider new representations. New affine representations which built on the spectrally flowed. So again, this W belongs, we'll take it to be positive, and there'll be the spectrally flowed vacuum such that we'll have mu R, mu dagger R, psi dagger 1, 2, R, and psi 3, 4 are all these acting on W is 0 for R. So once again, there'll be some only positive modes, some for these only for R greater than or equal to W plus 1 by 2 will the modes annihilate it. Below that, so there'll be the first W minus 1 by 2 modes will not. And similarly, the lambda R, lambda dagger R. So even some of the negative modes, what you might have thought of were annihilation operators, creation operators will now annihilate. It's very much in parallel to what I said over there. So what we have is, in other words, the modes, we can organize the modes. Via mu dagger alpha R, mu so these will lie in this wedge, same diagram like I drew before. So these will be creation operators and the canonical conjugates, which are also in this wedge, will be annihilation. So all these will be the wedge modes. So they are in this range, and we'll have the remaining modes. We can just abbreviate it in this way. And these will be creation operators. And the same thing with so these will be the out of the wedge modes. So so one way to maybe I could try to just illustrate it again a bit more. So for one set of operators like these mu's, mu daggers, and mu's, we have and we'll have creation. We'll have like creation operators up to here, and then there'll be annihilation operators here. So there'll be, so these will be annihilation operators, and these will be, that's for half the modes. For the other half, there will be the annihilation operators will be, well, I should sort of draw it on top of each other. and the annihilation operators are, sorry, and the creation operators are till here. So, so in the wedge there are equal number. I mean, you can see there are, these are, and so that half of them are creation operators, half of them are annihilation operators, and then outside the wedge it's the more normal pattern. So that's sort of just to illustrate this. And so that's what we have. We also have the action of spectral flow on the generators. Let me write some of them. So we can define the dilatation operator of the conformal group. That gets shifted somewhat like the way in which the J3, which was the dilatation generator in the original, in the ADS3 case, that got shifted. So this, if you wish, the space-time Hamiltonian. The central term C is unchanged. You can define, you can pick an R-symmetry and the R current, which corresponds to the spectral flow. Also gets shifted in this way. And the worldsheet Virasoro generator so you get something like this. So in fact, you can see this is the combination. This combination is what was shifting all the mode numbers. When I wrote this over here, this is, if you can check that this is nothing but this this combination. And you notice that this is a bit like, those who are familiar with these things may notice that this is a bit like the BMN Hamiltonian, which entered into the BMN picture story. And I'll say more about that next time. And the final point I just want to say before I stop is also to again notice that for W equals to 1, the wedge modes are the 0 modes, and generate the Raman sector. And just as this thing, as just to give you an idea of where we are heading, this W, this sector will actually label the number of words that are the letters that are there in the dual Yang-Mills theory. So once again, just like the spectral flow in the ADS3 corresponded to the length of the cycles of the twisted sector of the dual CFT, here it will correspond to the number of letters of the dual Yang-Mills theory. Okay, so next time we'll pick up from here about the quantization and the connection to the Yang-Mills spectrum and the BMN picture and so on. But if there are any questions, let me stop and ask.
Thanks, Rajesh. Questions?
Hi. Yeah. Sorry. Can you
two questions? Justin and Shomanshu. Yeah. Justin, you can start. Yeah.
Okay, yeah, this spectral flow, I mean, usually when we have a WCW model and we don't have the spectral flow, the states truncate at the level, right? Roughly speaking, the chiral primaries truncate at the level of the WCW. Like if there is
Right.
a
In the discrete, you're thinking of the discrete representations.
yeah, that truncates. So
Yeah.
this one allows you to go forever. I mean, this W.
No. Actually, I should have said that. I mean, not many people know this. That's why I didn't mention it. In the ADS3 case, in fact, it is truncated. In fact, it is very drastically truncated that only J equal to half representations are there. So in fact, even amongst the discrete, you remember the discrete ones, normally you go from J equal to half up to some K by 2 or K minus 1 by 2 or something like that, right? So now actually it is truncated exactly J equals to half. There's no other discrete representation. And in fact, so this is actually, it's more like a continuous representation rather than a discrete representation. So it's a special feature of the level 1 Weismann-Witten models for these things that the representations are effectively just there's essentially one non-trivial representation. It's a bit like SU2 level 1, which normally would have truncated up to K by 2, but for K equals to 1, it is just J equal to half. So there is just a single J equal to half primary.
So the discrete representation still truncate. I mean, there's no.
So in fact, there are no discrete representations.
Yeah, in this case.
In the level 1 theory. I mean, if you wish, there's a remnant of a discrete representation at J equal to half. It's really more like a continuous representation. It's not quite, I mean, the discrete and the continuous branches meet at J equal to half, all right? So this is that state in some sense.
Okay. Yeah, that was always in my mind. Yeah, okay.
Yeah, so that truncation is not there. I mean, in a way, well, it is subsumed under a more drastic truncation, which is that only J equal to half and its spectral flow images remain.
And just this, okay, I guess when we had the picture of this discrete, so I mean, you know, this the generators, I mean, the symmetry generators was like the sum of all these oscillators. We had to sum the bilinears to get the global generator. So here, right. I guess you have to just.
No, it will be somewhat similar because this is a current algebra. So you would be writing bilinears like I did I didn't write it explicitly for the ADS3, but it would be like this, right? So there'll be a sum. So of course, here it is in position space. So you have to do a discrete Fourier transform. This is in momentum space. So you have to do a discrete Fourier transform to position space to get something like this string bits.
Right, okay.
And then it will be exactly the same.
Right, okay. Yeah.
Because the global piece will be the m equals to 0 piece. So you'll get something like eta dagger r something in this one, there'll be a sum. And it will be a finite sum when you sum over the wedge modes. And it's these wedge modes that will give you this finite truncation.
Yeah, right. Oh.
So that's, yeah.
Yeah.
So it really gives a realization, I think, of the kind of model that you were trying to reverse engineer.
Yeah, so the question that I want to ask is that in ADS5, when you turn on the spectral flow, is there a semi-classical description of turning on windings of the strings, like Moldasina-Oguri's picture of ADS3?
Yeah, I think there should be, and this is something we are trying to work out some of the solutions. It's likely to be a little more complicated because the windings are now in twistor space, and they kind of descend to effectively some kind of coverings on the space-time, but it's a little more complicated. So I'm not 100% sure of the geometric picture, but indeed the spectral flow corresponds to locally they are creating winding in the target space, except the target space now is this ambitwistor space. The Ambi twistor space is some kind of a bundle over the of the target space over the ADS5, or this thing. You can think of it as some kind of spinor bundle over this ADS5, and so it's some wrapping in that whole thing, but it kind of descends, I think, to a covering map, some kind of a covering map. It's not, I think, a holomorphic covering map, but some kind of covering map on the ordinary space-time as well.
But winding in ADS5 is much weaker in the sense that, I mean, a string can unwind staying at the close to the boundary, whereas in ADS2 it's not possible, right? So
right. So that's why the spinor part is very important. I think in the twister, it's not just the ADS5. There is this additional twister piece, which has a P1, which has actually two P1s in them. So it can non-trivially wind on the P1.
I see.
This is something. It's still sort of this is the thing with Pranabhesh and Faizan and so on. We are trying to nail down. It's sort of a little elusive. I mean, there are a few things which are. I think many things have fallen in place. I think one or two things have not yet fallen in place.
And I have a follow-up question on what Justin was asking. So the shortening of the long multipliers at k equal to 1, the same conditions here in ADS5, the conditions are almost the same that you have in ADS3, exactly the same.
Yeah. So if you embed the, I mean, so there is effectively a shortening of the representations here also. I mean, if you think of the SU1, embedded inside the SU2, then effectively that J for that SL2R subgroup is restricted to be J equal to half.
Okay.
Yeah, it's essentially this magic of the level 1 theory. Same thing here. So you might have asked, I mean, you might have asked why, I mean, so in the case of ADS3 times S3, there was sort of a good reason why you had a PSU1,1/2 at level 1, because there was an NS flux, and so that gave you the three-form flux, and that gave you the Weismann-Witten model. Even in the hybrid formulation, that was sort of the reason. So the analogous statement here, I don't have a very good answer for why we get a level 1 theory. In some ways, it's like some, I mean, but it's kind of a topological theory, so maybe there isn't a real geometric interpretation. In some sense, it has zero flux in terms of Ramon flux. If you wish, lambda equals to 0 is where there's in some ways no flux. I mean, there is n units of flux, but it doesn't back react on the geometry. But I think in some way this PSU2,2/4 at level 1 seems to be kind of the piece which is which captures that tensionless limit in some. It's a barely physical theory. I mean, it's a topological theory. That's why I think it's sort of barely there. And as you turn on the coupling, it starts becoming more complicated and more.
And this theory, when we turn on, I mean, the people have studied the theory, like the beta function and so on.
Yeah.
As a closed sigma model, I mean, closed string sigma model.
You mean the PSU2,2/4? Yeah, it's an exact sigma model. That's something which is known that the supergroups. This is an exact sigma model. In fact, you can say more for the supergroups that the coefficients of the Weismann term and the usual kinetic term can be varied independently, unlike that of the ordinary groups. And they still continue to be conformal for something like this, because the second Casimir actually vanishes of these supergroups. So the beta function is identically 0 even when you change the two coefficients. So it's not only at the Vesumino point, but elsewhere also you can define this. And this had an interpretation in the ADS 3 times S3 that this was the thing that kind of, by changing the relative coefficients, you could turn on the Ramon flux. In ADS 5, I don't know what is the corresponding interpretation, but that is something you can do in the sigma model in principle. You can change the relative coefficients. It may correspond to some beta deformed or one of these deformed Yang-Mills theories. I suspect, but I'm not very sure.
Does it changes the isometry? I mean, because
no, it doesn't. It doesn't change the isometry because it's still PSU2 comma, at least at naively, I don't think it, yeah, it doesn't change, I think, because the PSU2 comma 2/4 is preserved. That is true for these beta deformed theories also, right?
Like, no, beta deformed, I mean, the S5, for instance.
Like, they get squashed and all that.
Squashed, yeah.
Yeah. So I don't know. I don't know what it corresponds to here. I mean, if it does make sense at all. Or maybe it just corresponds to some other.
Interesting to study them also. Yeah.
Huh?
It's interesting to study them. I mean,
yeah.
At
least in perturbation theory, one should be able to study turning on a slight this thing. In fact, for the ADS 3 times S3 itself, it is interesting to do that with this k equal to 1 theory, to make it 1 plus epsilon and 1 minus epsilon, the two coefficients. And that would correspond to turning on the Ramon background in ADS 3. And I think that is an interesting perturbation of the tensionless string theory, because in fact it is that perturbation by which you can go to the large radius limit, because the Never-Schwarz flux is quantized, so you can only go by discrete this thing. But if you turn on the Ramon flux, that is not quantized, and so by turning that on and then flowing to infinity, you can go to the large radius limit. So many of these things that we find, like the delta function localization of correlators, they probably will get smeared out when you kind of turn on that perturbation. But it's likely to be a singular perturbation in some ways also. So it's a very delicate, it's probably a very delicate perturbation expansion.
But the continuum will still be absent, or it will just show up?
The continuum should be absent, I think, because at least on physical grounds, it should be absent, because now the light objects are only some kind of PQ strings or something like that,
I see.
Not fundamental strings.
Right.
Any other questions?
Next lecture on Friday, is it? I mean, I have to.
No, Thursday. Yeah, that's a good
Thursday,
point. Yeah,
no.
We'll send a reminder. Don't worry. So it's Thursday from the same time. Oh, what happened?
You're talking, isn't it?
Oh, damn! I forgot. Yes.
I mean, come on.
Let me just stop recording.
There was another talk like this.
Yeah, sorry. I completely forgot what. Yes. Sorry.
No, we have some faculty seminar, and Anindya is talking this time.
Oh, I see. On Thursday.
Yeah.
Sorry. Completely forgot. It's my bad.
Can
we prepone Rajesh's talk on that day, or?
Yeah. Okay.
Rajesh, how are you placed? Say
Thursday.
From 2 to 3:30.
Sorry.
From 2 to 3:30, can we make your talk from 2 to 3:30?
2 to 3:30. Yeah, 2 to 3:30 should be okay.
Okay. So everybody, hopefully you heard, and we will send out an announcement as well. Yeah, thanks Justin for reminding. Otherwise, I would have missed my own seminar.
Another one. Yeah, okay.
Yes, I forgot. Yeah, let me stop recording. Anyway, my cursors were all recorded.